Good morning, good afternoon. Recently, I was reading about the shark frenzies after they laid the first fiber optic underground transatlantic cable near the Canary Islands. And of course, the sharks were attracted or sensed the electrical radiation and of course were electrocuted by the high voltage power, but not before causing prolonged outages. Now, I don't think in the cable industry we're too concerned about shark bites, but possibly squirrel chews. My point is that during this presentation we'll show how even one leak can be responsible for making an entire node inoperable. The general consensus now in North America is that there is one significant leak per mile or kilometer of plant. So if you have 20,000 miles of plant, you've got 20,000 leaks. If you've got 10,000, you've got 10,000 leaks. How are you going to fix that many leaks? You can't. So we're going to talk about a method of prioritizing or mitigating those leaks. I'm going to mention what the 5 are, and then we'll go through each individually. The first method is that when measuring, you need to measure, if you're concerned about LTE, you need to measure within the LTE bandwidth. Today, many companies will measure near LTE. And one of the reasons for that is the 605 megahertz channel is a quiet channel. It's astronomy. It's easy to use. But it's 150 megahertz away from LTE. Now what happens is that if you're concerned about a leak at LTE that could be, and we're going to show an example here, 115 microvolts per meter, that could present as only 150 megahertz away. So the first one is you need to use a relevant channel. The second method is to tie the LTE signal strength along with the leak level as opposed to the tower location. A major operator in the States asked us to put the tower locations on the maps where we're showing the leaks. We said, why do you want to do that? And I'll show you why. It doesn't make sense to have the tower locations. It does make sense to have the LTE signal strength relative to the leak. The third method is with respect to using node maps as a driver that show the QAM signal level, because for every 1 dB decrease in QAM signal, you will get a 2 dB decrease in CNR. And with a very low QAM signal, even hundreds of feet away from the tower, you can have a leak that will affect downstream every subscriber with constellation fuzziness, mirror degradation, but for every downstream subscriber with only 1 microvolt, 150 meters away. The fourth method will be to take a look at the power of proactive network maintenance along with the forward capture modems, D3, 3.1 for plant troubleshooting. And the fifth will be a direct correlation of the LTE downlink frequencies with forward ingress. So we're going to talk about those. Last year in the United States, the FCC auctioned $55 billion of spectrum to Verizon, AT&T, and some others. So the telco owns the spectrum. He owns it. He owns it. He owns it. There's much publicity in the United States today about issues with respect to cable companies egressing on the tower. But we're going to show that more frequently or more prevalently are ingress issues from the telco to the cable plant. Two scenarios we're going to take a look at it for a moment are the concept of the aeronautical frequencies and the issues of the LTE frequencies. One is that for the last 30 years, the industry has done a commendable job on aeronautical frequencies with CLI compliance as a compliance issue, not as a network maintenance issue. And what happens is that generally low frequency issues are drop related. High frequency issues are hardline related. We've had no visibility to those hardline problems. And The main origination of this, of course, was that for the aeronautical compliance was so that airplanes won't crash. Well, how many airplanes have crashed in the last 30 years because of leaks from the cable plant? 0. At the same time, those leaks do represent a potential for disrupting communications, aircraft communications, that form audible noise, static, buzzing, but nothing to the extent of system failure, because the symptoms are long recognized before it can reach a level like that. But in order to comply, again, we've been doing a great job on the low frequency side without any visibility to high frequency. Until there was one widely advertised, proclaimed situation in 2010 by a leak from a cable system affecting Verizon. And Verizon has a very loud mouth, and rightly so. In this particular case, they were using analog equipment. It was a recently deployed LTE location service. There was a lot of hoopla about it. And before you knew it, 60% of the coverage was gone. And they did have analog detection equipment. The analog detection equipment showed that there was a leak of maybe 10 microvolts. In fact, what happens is if the RSSI, the received signal strength of the telco, exceeds minus 90 dBm, it automatically triggers an investigation. And what happens when the telco starts an investigation, the ad hoc activity is that they use the espionage type Rodian Schwartz, very sensitive panoramic receiver, and a spectrum analyzer that shows you the starting point that physically locate where the problem is coming from, and Yagi antenna. And basically, they use the base station sector antenna coverage that gives that alarms on which base station has been affected. So you go to that area, 500 meters from the antenna, looking at passives and amplifiers and cabinets, and using mapping software, get the GPS coordinates, and write a love letter to the cable company, remove that channel, or fix the leak, and do it immediately. So it's a very significant situation when you consider the numbers of leaks that we're talking about here. So since that well-publicized event, there have been hundreds. Just Google LTE leaks, as you know, 600. Well, first of all, 600, 700, and 800 megahertz should be a closed network. But if the shielding integrity is degraded or compromised, outside signals will leak in and disrupt the sensitive electronics. Inside signals will leak out, and you get coverage problems, connectivity problems, dropout problems on the telco side. So that this is a real world problem with respect to shielding. In the meantime, since that study, and then we get on with our prioritizations, there have been a number of well-publicized studies and papers, some written by gentlemen most of you know here, Ron Rannick with Cisco. He's written many papers. Ray Thomas, originally with Comcast, then went to Time Warner. The Rodian Schwartz white papers. Virgin Media, that was 2009, was a very large study on set-top boxes and cable modems with a headset or with the handset transmitting at very high power and very close proximity to the CPE equipment, showing the onset of uncorrectable errors, pixelation, all kinds of problems, off-gam studies, ANGA studies, Rogers in Canada in 2012. So it's a lot of data on these studies globally. The fact is that towers continue to be built. Trivia question. Anybody guess how many towers were built last year in the US alone? Telco towers. Just a guess.
10,000.
20,000. Close. In fact, it's been for the last 10 years, if you look at the statistics, it's been about 20,000 per year. It's not going this way, but it's 20,000 a year. Core frequency usage issues continue to increase. As you go to higher and higher formats, modulation formats, the susceptibility to noise increases. And usually the interference, it's gradually, or it severely degrades until you get a cliff effect. It just suddenly, it's not a gradual, suddenly you have a very serious issue. And with DOCSIS 3.1, the SNR requirement now is 20 dB greater than legacy systems. So there are more and more leaks, and not just the Edward Snowden types. So first we're going to I'm going to show this schematically in a second. I'm just showing the meter, okay, and what happens. Well, let's show. Oops. Let me just show how this thing works. We've got a processor at the head end. We're down converting a sample of a true QAM channel. We're taking its IQ, phase amplitude, all the features of a real channel, down converting its signature, sending it by IP to a field meter. The field meter receives it, and at the same time has an RF antenna that's pulling from terrestrial, seeking the signature of a leaking channel. And when it finds it, it does an autocorrelation that detects a leak, and then it does a time distance of arrival, TDOA, which is the E911, to pinpoint exactly where that leak is. Now remember, that leak has left the head end over fiber, over coax, to the leak location to the meter. So the shortest distance to the leak will be the over-the-air portion. These are the kinds of problems that we're looking at. There's really four types. You've got the cable company that's egressing against the tower. 20 microvolts per meter is enough to start degradation of the noise floor of the tower. 50, which isn't a lot, 50 microvolts is enough to trigger an investigation. And we already described what happens during an investigation. Also, it's important to know here that frequently the leak or the impairment, it may be in an enclosed cabinet, so there's no physical damage. So you may need to be able to resolve to 1 inch to find that faulty connector. So you need to have a precision type detection equipment. The second type is from the egressing the cable plant, egressing the headset, the hand phone. And in this case, 50 microvolt at 3 meters, which is reasonable, is enough to affect the noise floor of the smartphone. The third one is more prevalent, which is the ingress from the tower to the cable plant, where, again, we're going to show some charts on this. On just 1 microvolt is enough to cause a very severe problem. And of course, the other way is from the headphone, from the handset to the cable plant, where Ron Rannick has shown in a case with the phone transmitting at plus 23 dBmV with far from the tower, close proximity to electrical wiring with a very low QAM signal, has the effect of generating 2.2 volts, not microvolts, volts per meter. So here's 2 examples on the ingress side. On the left-hand side, we're showing that the phones are transmitting far from the tower, again, under the conditions. This is on the uplink frequencies, on the conditions, again, of the poor QAM signal. Over on the right-hand side, we're showing that the tower, in close proximity to the home, will affect all subscribers downstream from that home. So when we talked about down-converting the signature of 1 channel, really, we're going to emphasize through this presentation, you need to do 3 channels. And the reason, if you look back on what we talked about Verizon, they had an aeronautical leak detector that wasn't able to find a leak that was 2,200 microvolts per meter. You need to measure simultaneously in the low band, in the mid band, and the high band, all at the same time. So what your meter will show is the output of the leak level and its time delay and the channel and some other data. I'm just showing you some summary data here. So this is a typical drive out. In this drive out, what we're trying to show is how the time delay varies in small amounts and how the signal level varies in small amounts. Because the green dots, the green markers are suggesting there's not enough information to tell you there's a leak. The pink dots, yes, I found a leak, but I don't know enough about it to identify it. Red dots, I found a leak. 3 red dots at least, and you've confirmed that it is a leak. On the client, you can click on any of these markers and you get a lot of data. I'm just showing some of the data here. But for example, the highest leak level and the lowest time delay, this will output the flag. So this point and this point should be over each other, but due to imperfections of the antenna, geographic, some other considerations, not exactly, so it will give you a tolerance within 5 meters or 10 meters scaled for that leak. And looking at this data here, you see the time delay is 103.12, 102.98, 102.98. So these are very, very close. So we're taking a delta time delay at one marker, time delay at another. We're doing a delta between the two time delays, and then the processor will do a complex equation solution to pinpoint exactly the GPS coordinates of that flag. Significantly, there is no multipath reflections, which is a big problem with analog type devices of leaks bouncing against buildings, getting multiple leaks, because this technology filters everything out and just shows that maximum leak level. Also, there's no issue with the speed or Doppler effect, because with the analog systems over the last 30 years, as you know, you drive along at 30 miles an hour. But we just mentioned that a lot of these problems are hardline problems. So it's a little bit difficult to drive 30 miles an hour on the highway if you're down looking at for trunk type issues. So this technology will allow any speed. There's no Doppler effect. These flags here, these are two systems in New York that are right beside each other. These are thousands of leaks from that one plant. Now, any noise that finds its way into the cable plant has the potential of disrupting the capability of 3.1 maximizing. And what's happened is that technology has squeezed so much bandwidth into the cable system that the noise susceptibility is increased. So we're going to show a number of prioritization methods on how to pinpoint or how to prioritize which leaks need to be affected. Here we're looking at some studies that we did on over 3,000 leaks, which means over 3,000 miles of plant. So if you were to look at this prior to the prioritization concept that we're talking about, you would say, well, let's fix all the big ones. Well, it's not a matter of bigger being worse necessarily, because remember, we're looking at egress and we're also going to be looking at ingress. So, So we've also mentioned that particular leak that's only 1 microvolt. So if we're only looking at the high amplitude leaks, we're not going to get a full picture. So in this case, we're looking at aeronautical. We're looking at aeronautical frequencies compared to, in this study, compared to LTE leaks. Now, we've been doing all this great work for the last 30 years, so we're not surprised to see that there's not an awful lot of leaks on the drop side. We shouldn't be surprised to see that there are a lot of leaks on the high frequency side, because we haven't addressed them. We haven't had the visibility. It's been a reaction. It's been proactive. It has not waiting for truck rolls, if you like. Whereas in this case, we're showing that a very small amount of the leaks actually were aeronautical types, and yet 67% of the leaks were high frequency. However, on the point of making sense to look at multiple frequencies, we're showing, sure, you got leaks at low frequency, you've got leaks at near LTE, and you got leaks at LTE frequency. But generally, the larger the leaks and the more prevalent leaks seem to be on the high frequency side. So if we decided, in this case, we've addressed the aeronautical type frequencies, so I want to focus on the near LTE type frequencies. Because when we say high frequency, again, I want to make a clear differentiation between near LTE and LTE. So, making a comparison at 609, which again is this very popular astronomy channel that people like to use, compared to 789, which is well within the LTE. In this case, we're showing that Again, you have leaks at near LTE and at LTE, but generally all of the lines slope towards the high frequency side. So that if we decided just to look at the near LTE type leaks, we would have in this particular case 8%, and if we were to look at only the high frequency side, we would have 37% of the total. So finally, on this series of comparisons, suppose we were to clean up all of the leaks greater than 20 microvolts per meter that were at the near LTE side. Well, guess what? We would still be left with all of these high frequency leaks, a large number of them, very large leaks, and we're going to show one particular example that focuses on why this is very important. First of all, we'll take a look at a number of examples. Each of these examples, before we focus on another Verizon complaint, will show you leaks that were not found with analog testing equipment at aeronautical frequencies and were found at LTE. Here's a case, cracked tap housing, 158 microvolts per meter. This one was a burnt out tap with the suck out. Again, high frequency. It didn't show at all as a problem on low frequency. Here's another one. Very often, by the way, we're able to see right from the Google Maps because of the accuracy of the time distance of arrival concept, you're able to actually see the leak and fix it just while you're doing the drive out. Here's another radial crack in a feeder cable, a crimp on a connector. So we're going to talk about this one for a moment. This particular case was a complaint for Verizon, and it was a defective tap. Now we asked Verizon if we could play with that tap and figure out what was going on. And what was happening was that it had a mesh RFI braid seal that was defective. And as we looked at it, it made it look as though the top and the bottom of the tap were electrically isolated by 200 ohms, and it was supposed to be a short circuit. So the performance at 150 megahertz was great, aeronautical frequency. But this is what happens, because as you increase in frequency, the shielding effectiveness gets worse, of course. Now, this leak was not detected, as I mentioned, at aeronautical frequency because the shielding effectiveness was okay at 100 dB. However, at LTE, 700 megahertz, the shielding effectiveness was pretty poor. Now, we did the comparison here at near LTE and LTE just to prove a point. At near LTE, at this popular 600 megahertz frequency, the shielding effectiveness was better by 18 dB plus a 2 dB slope, so it was like 20 dB. Yet, at 700 megahertz, it represented as 112 microvolts per meter. At 600, it was only 14. So the technician who was responsible for addressing this leak, if he had just used a near LTE testing, which a lot of the industry does, and he's charged with making a repair or an ignore decision, he would have ignored it. It's only 10 dB. So we're trying to emphasize here what the importance of measuring within a relevant frequency. Again, this is a if you have good shielding, you shouldn't have any problem with over the air carrying the same signals as a cable channel, but at the same frequency carrying different signals. But that's not the case. So what we're showing here on yellow is the performance of that defective tap. Blue is after we fixed the tap. Purple was the performance of a competitive tap we had in the lab. And at the very bottom here is the actual performance of the G-temp chamber itself. So you see how all of these varied. Now, in summary, on that particular chart about the relevant frequency, it makes a huge difference that you either, if you're concerned about LTE, measure within LTE, not near it. Okay. What we're trying to show here is this is a drive out of 3 minutes. And it's clear from this chart that if you look at the LTE signal strength, that any leaks that have a high signal strength needs to be repaired. Any leaks that have a very low do not need to be repaired. And here's why. We are detecting for leaks every second. But in actual fact, we were only detecting for 2% of that minute. So we're 98% of a minute just going to waste, just sitting around. Now, this large cable system in the US asked us to put the tower maps on the maps where we show the leaks. And we said, why do you want to do that? Because it's more important to show the LTE signal strength relative to the leak than the base station tower. And I'm going to show you how we do that in a moment. In the meantime, this is what we did with the rest of that second. First of all, we take the QAM leak measurement, and then we take all of the QAM channels that are co-frequency to the downlink frequencies and the public safety channels. We scan and tune through all of them, and we record the maximum signal from the LTE, and then we use that as a driver, along with the database, the leak database of leak levels and the locations and the latitude and longitude. Now we add another set of sorting data of the LTE leak level. And for example, in this case, you have a 282 microvolts per meter leak. Well, looking at one of the earlier charts, I say that's one you'd automatically go to fix. But the LTE level is minus 89 at that point. So who cares? That leak isn't going to do anything. Now here you have a 790 microvolts per meter leak and a minus 60 dB. So you're more concerned about that one. It's just offering you more information in order to make a decision. This is how we did that measurement. We looked at 18 hub sites, and our objective was to show how our LTE signal level method compared to a spectrum analyzer. We used an Agilent in this case, and we also wanted to show, was there a direct correlation on the proximity of the detector to the tower? And we went to the location. We took a 10-second max hold with the Agilent, then we switched the antenna input to our device. Overall, we found we were getting faster responses because of our FFT spectrum analyzer, and we were able to capture quicker OFDM signals. But there was an overall very loose correlation of the data because of the low trend of the slope line and because of the widespread of the data. But this is kind of what it showed. Now we're trying to show, is it important to show the actual location of the tower with respect to the leak? So we said, oops, at 280 feet, we had a leak that was minus 40, which was pretty bad, suggesting you do need the tower. But wait a moment. At the same distance, you had a leak that was way down at 68. So what's this telling us? Nothing. Now we looked at another example at 100 feet from the tower. And these would be the same. This would be the same as using the Google Maps for if we were to put the maps on our own database. You had a leak that was close to the tower that was minus 52, suggesting maybe the tower is important, but again, at that same level at 720 feet, you have the same leak level. So there's no correlation in the data, probably because of all of this stuff. The antenna beam direction, lobes, tower heights, geographic considerations, making it. So it was more important to show the strength than to show the actual location of the tower. The third method is the tower's ingress effect on the CNR, cable CNR, because of the signal of the QAM signal level. For example, if you have a very strong signal, QAM signal at the output of an amplifier at 40 dBmV, even a 500 microvolt per meter leak at 150 meters away will have no effect on the CNR. even, I'm sorry, 1,000 or 150, etc. However, even 1 microvolt at 150 meters, if you have a poor 10 dBmV at the input of the amplifier, has enough of an effect of causing, again, constellation fuzziness, degradation in myrrh and burr, but on all downstream subscribers. So even hundreds of feet away from the tower, a very small leak, if you have a poor cram signal, will be devastating. Hence, the driver is to use node maps, and on the node maps, we're showing the devices, and this matrix doesn't show it, but we'll show the nodes as well as showing the LTE signal level. We'll also show the node, and we'll show the actual device that's causing that leak. And the reason that that is so effective is because of the accuracy of the time distance of arrival, which again uses, at one point you're taking a time delay reading, and at another point, and somewhere of the delta between these two on this hyperbola, there's a leak. You need 3 points for triangulation at least. So between these 2 points on this hyperbola, somewhere there's a leak. Where they intersect will be the actual leak. Of course, there's a 4th point and a 5th and an nth point as you get closer and closer to the leak location. And then it outputs the leak level and its time delay, and it also outputs the leak flag on the screen of the heater. The 4th method is to look at the technology today makes it so easy to look at the forward response, so full forward of wideband cable modems, 3.3, 3.1. And the power of proactive network maintenance developed by Cable Labs is to troubleshoot for forward ingress and along with other impairments. And forward ingress will manifest as inhabiting the same code channel as the downlink frequency, so that in this case, we're looking at a Comcast Scout Flux screen that says, yes, you've got ingress, the presence of ingress, and yes, it's at these frequencies. So now you know you have an ingress problem, a forward ingress problem. Well, where is it? Well, if the CMTS is telling you that these 15 modems are being affected, well, you know you've got all of these leaks in that area. So you go to the next forward capture modem and you see if you still have ingress. Well, then it wasn't caused by a leak between those two. You go to the 4th one, the 5th, to the nth cable modem. That's tell you, oops, I don't have ingress. Well, you know now it's between here and there. So you've narrowed the list of candidates. You've ignored a whole bunch of leaks in between. Now you can do the prioritization of the other features that we talked about, of the few leaks that are remaining. Now you look, do they have a high QAM signal, or do they have a low LTE? Because if it's a very low LTE level, then it's not going to do anything. So you're able to prioritize further. So basically what that chart has said is that you query the modems and look at the frequency response of the downlink. Is there forward ingress? You look at the upstream locations of the node map showing the variables we talked about. Then you select those locations most likely to be the source and dispatch a technician to fix it. The 5th method is automating the one we just mentioned. What we're doing now is we're sending a technician to a location that's been identified by the CMTS as a location problem area where modems are being affected. Without getting out of the car or doing anything, he hooks the meter in, and he is accumulating LTE downlink samples. He forwards those samples to a PNM server, and the PNM server is pinging the cable modems in the field for the presence and location of forward ingress. And it's also acquiring RF samples from the database with the maps that have been exported from the cable company into the leak database, looking at the downlink, the same downlink frequency, looking at the leak levels, looking at the devices that are causing these leaks. And the system does an autocorrelation that the downlink frequencies that have been identified as the trouble area, and the downlink frequencies that are causing the problem are the same. At that point, the technician knows, go fix it or ignore it if they're not the same and go to the next one. All we're showing here is that this technology uses a true QAM channel. It doesn't inject a carrier. You inject a carrier between QAMs and you don't know what might happen because you're introducing some instability. Also, that approach is an estimated approach. This is a calculated approach. You're calculating exactly where the leak is. And it's also OFDM future-proofing, because you can put that 6 megahertz anywhere in the 192 megahertz, which is difficult with other technologies. So, in summary, there are 5 prioritization methods because there are so many leaks. And I'd be happy to address any questions you may have. Oh, by the way, I had to close. You have to have a funny close. Without telling my age, of course. But some of my classmates are saying, you know, there are some leak mitigation personal techniques that I'd like some advice on. But we're not addressing those kinds of leaks. Okay, thank you.